Hello all. In today's lecture we are discuss about age models. Age detection is the approach used most frequently for segmenting images based on abrupt, that is local changes in intensity. We begin by introducing the several ways to model age and discuss number of approaches for age detection. Age model are classified according to their intensity profile. Age model is classified into the three types, that is step age, canny age model and roof age model. A step age involves a transition between two intensity levels occurring ideally over a distance of 1 pixel. Canny age detection is a technique to extract useful structural information from different vision objects and dramatically reduce the amount of data to be processed. It has been widely applied in various computer vision systems. And the third model of and is the so-called roof age. Roof edges are models of lines through a region, with the base of roof edge being determined by the thickness and sharpness of the line. Let us considering the one example, that is in image generated by a computer for a use in areas such as solid modeling and animation. These clean ideal edges can occur over the distance of 1 pixel, provided that no additional processing such as smoothing is used to make them look real. Digital step edges are used frequently as age models in algorithm development. In practice, digital images have edges that are blurred and noisy, with a degree of blurring determined principally by limitation in the focusing mechanism, for example lenses in the case of optical images, and the noise level determined principally by the electronic components of the imaging system. In such a situation, edges are more closely modeled as having an intensity ramp profile. The slope of the ramp is inversely proportional to the degree of blurring in the edge. In this model, we no longer have a thin 1 pixel thick path. Instead, an edge point now is a point contained in the ramp, and an edge segment would then be set of such points that are connected. Roof edges are models of line through a region, with the base width of roof edge being determined by the thickness and sharpness of the line. In the limit, when its base is 1 pixel wide, a roof edge is really nothing more than 1 pixel thick line running through a region in an image. Roof edges arise, for example, in range imaging when thin objects such as pipes are closer to the sensor than their equidistant background, such as wall. The pipe appears brighter and thus create an image similar the model in figure, as shown in figure C. As mentioned earlier, other areas in which roof edges appear routinely are in the digitization of line drawings and also in satellite images, where the thin features such as road can be modeled by these type of edges. It is not unusual to find images that contain all three types of edges, although the blurring and noise result in deviation from the ideal shapes. Edges in images that are reasonably sharp and have a moderate amount of noise do resemble the characteristics of the edge model in figure, as shown in figure. As the profiles, what the model in figure allow us to do is write mathematical expressions for edges in the development of image processing algorithms. The performance of this algorithm will depend on the differences between the actual edges and the models used in developing the algorithms. This figure represents a 1508 by 1970 image showing zoom, actual ramp, bottom left, step, top right and roof edge profile. The profiles are from dark to light in the areas indicated by the short line segment shown in the small circles. The ramp and the step profile span 9 pixels and 2 pixels respectively. Then the figure 10.10a shows that the image from which the segment in figure B was extracted. The figure B shows the horizontal intensity profile. This figure shows also the first and the second derivative of the intensity profile. As in the above discussion, the moving from left to right along the intensity profile, we note that the first derivative is positive at the onset of the ramp and at points on the ramp, and it is zero in the areas of constant intensity. The second derivative is positive at the beginning of the ramp, the negative at the end of the ramp, and zero at the point on the ramp, and zero at point of a constant intensity. The sign of the derivatives just discussed would be reversed for an edge that transition from light to dark. The intersection between the zero intensity axis and a line extending between the extrema of the second derivative marks a point called the zero crossing of the second derivative. We conclude from these observations that the magnitude of the first derivative can be used to detect the presence of an edge at a point in an image. Similarly, the sign of the second derivative can be used to determine whether an edge pixel lies on the dark or light side of an edge. We note that the two additional properties of second derivative around an edges, that is, it produces the two values for every edge in an image, and undesirable features. And second one is its zero crossing can be used for locating the centers of the thick edges. As we show later in this section, some edge models make use of the smooth transition into and out of the ramp. However, the conclusions reached using those models are the same as with an ideal ramp, and the working with the latter specifies the theoretical formulations. Finally, although attention thus far has been limited to a 1D horizontal profile, a similar argument applies to an edge of any orientation in an image. We simply define a profile perpendicular to the edge direction at any desired point and interrupt the result in the same manner as for vertical edge. We conclude from these observations that the first derivative can be used to detect the presence of an edge at a point in an image. The sign of a second derivative can be used to determine whether an edge pixel lies on the dark to light side of an edge. And the additional two properties of second derivative around an edge, it produces two values for every edge in an image, and its zero crossing can be used for locating the center of the edges. The image segment in the first column in figure shows close-ups of 4 ramp edges that transition from the black region on the left to the white region on the right. Keep in mind that the entire transition from black to white is a single edge. The image segment at the top left is the free of noise. The other three images in the first column are corrupted by the additive Gaussian noise with a zero mean and standard deviation of 0.1, 1.0 and 10.0 intensity levels respectively. The graph below each image is a horizontal intensity profile passing through the center of the image. All images have 8 bits of intensity resolutions with 0 and 255 representing black and white respectively. Consider the image at the top of the center column as discussed in connection with figure B. The derivative of the scan line on the left is 0 in the constant areas. These are the two black bands shown in the derivative image. The derivative at the point on the ramp are constant and equal to the slope of the ramp. These constant values in the derivative images are shown in gray. As we move down the center column, the derivative becomes increasingly different from the noiseless case. In fact, it would be difficult to associate the last profile in the center column with the first derivative of a ramp edge. What makes this result interesting is that the noise is almost invisible in the images on the left column. These examples are good illustration of the sensitivity of derivative to a noise. As expected, the second derivative is even more sensitive to the noise. The second derivative of the noiseless image is shown at the top of the right column. The thin white and black vertical lines are the positive and the negative components of second derivative. As explained in figure, the gray in these images represent 0. As discussed earlier, scaling causes 0 to show as a gray. The only noisy second derivative image that barely assemble the noiseless case is the one corresponding to a noise with a standard deviation of 0.1. And the remaining second derivative images and profiles clearly illustrate that it would be difficult indeed to detect their positive and the negative components, which are the truly useful features of the second derivative in terms of edge detection. The fact that such a little visual noise can have such a significant impact on the two key derivatives used for detecting edges is an important issue to keep in the mind. In a particular image, smoothing should be a serious consideration prior to the use of the derivatives in application, where the noise with the levels similar to those we have just discussed is likely to be present. We conclude this section by noting that there are three fundamental steps performed in edge detection. First one is image smoothing for a noise reduction. Next one is detection for edge points, and last one is edge localization. These are the three important fundamental steps that are used to perform for edge detection. Next topic is basic edge detection. For detecting the changes in intensity for the purpose of finding edges can be accomplished using the first and the second order derivatives. First point is the image gradient and its property. The tool of a choice for finding the edge strength and direction at the location x, y of the image f is the gradient denoted by del f and defined as a vector, that is the del f is equal to gradient of f is equal to matrix of gx gy is equal to matrix of del f by del x del f by del y. This vector has the important geometrical property that it points in the direction of the greatest rate of change of f at a location x, y. The magnitude means the length of the vector del f is denoted by m of x, y, where m x, y is equal to magnitude of del f is calculated by using under roots of gx square plus gy square. Is the value of the rate of change in the direction of the gradient vector. Note that gx, gy and m of x, y are the images of the same size as the original, created when x and y are allowed to vary over the all pixel locations in f. It is a common practice to refer to the latter image as the gradient image or simply as the gradient when the meaning is clear. The summation, square and the square root operation are the array operations. The direction of the gradient vector is given by the angle, that is alpha x, y is equal to tan inverse of determinant or tan inverse of matrix of gy upon gx measured with respect to x axis. As in the case of a gradient image, alpha x, y also is an image of the same size as the original, created by the array division of image gy by image gx. The direction of an edge at an arbitrary point x, y is orthogonal to the direction alpha x, y of the gradient vector at the point. The figure A shows a zoom section of an image containing a straight edge segment. Each square shown corresponds to a pixel. And we are interested in obtaining the strength and the direction of edge at the point highlighted with the box. The pixel in a gray have a value 0 and the pixel in a white have a value 1. We show the following this example that an approach for computing the derivative in the x and y directions using a 3 by 3 neighborhood center. About a point consists simply of subtracting the pixel in the top row of the neighborhood from the pixel in the bottom row to obtain the partial derivative in the hood from the partial derivative in the x direction. Similarly, we subtract the pixels in the left column from the pixel in the right column to obtain the partial derivative in y direction. It then follows using this difference as our estimate of the partial, that del f by del x is equal to -2 and del f by del y is equal to 2 at the point in a question, then del f is equal to matrix of gx gy is equal to matrix of del f by del x del f by del y is equal to matrix including the value -2 2, from which we obtain m of x comma y is equal to 2 root 2 at that point. Similarly, the direction of the gradient vector at the same point follows from the equation alpha x comma y is equal to tan inverse of gy by gx is equal to -55 -45 degree, which is the same as the 135 degree measured in the positive direction with respect to the x axis. The figure B shows the gradient vector and its direction angle. The figure C illustrates the important fact mentioned earlier that the edge at a point is orthogonal to the gradient vector at that point. So the direction angle of the edge in this example is alpha is equal to alpha minus 90 degree is equal to 45 degree. All the edge points in the figure A have the same gradient. So the entire A segment is in the same direction. The gradient vector sometimes is called as the edge normal. When a vector is normalized to unit length by dividing it by its magnitude, the resulting vector is commonly referred to as a edge unit normal. Then the next topic is gradient operator. Obtaining the gradient of an image require computing the partial derivatives del f by del x and del f by del y at every pixel location in the image. We are dealing with the digital quantities. So the digital approximation of a partial derivatives over the neighborhood about a point is required. We know that gx is equal to del f of x comma y upon del x is equal to f of x plus 1 y, comma y minus f of x comma y, and gy is equal to del f of x comma y upon del y is equal to f of x comma y plus 1 minus f of x comma y. This equation we are already studied in previous lectures. These two equations can be implemented for all the pertinent values of the x and y by filtering f of x comma y with a 1D marks as shown in figure. When the diagonal edge direction of the interest, we need a 2D mask. The Roberts cross gradient operator are one of the earliest attempt to use the 2D marks with a diagonal preferences. Consider the 3x3 region in this figure A. The Robert operator are based on implementing the diagonal differences of g of x is equal to del f by del x is equal to z9 minus z5 and g of y is equal to del f upon del y is equal to z8 minus z6. This derivative can be implemented by filtering an image with the mask in figure B and C. The marks of a size 2 by 2 are the simple conceptually, but they are not as useful for computing the edge direction as the marks that are symmetric about the center point, the smallest of which are of size 3 by 3. These marks take into account the nature of the data on opposite side of the center point and thus carry the more information regarding the direction of an edge. The simplest digital approximation to the partial derivative using the marks of a size 3 by 3 are given by, that is, g of x is equal to del f by del x is equal to z7 plus z8 plus z9 in one bracket minus in another bracket z1 plus z2 plus z3, and gy is equal to del f upon del y in first bracket z3 plus z6 plus z9 minus in second bracket z1 plus z4 plus z7. In these formulations are the difference between the third and the first row of the 3 by 3 region approximates the derivative in the x direction, and the difference between the third and the first column approximation the derivative in the y direction. We would expect this approximation to be the more accurate than the approximation obtained using the Robert operator. These both the equation can be implemented over an entire image by filtering f with the two marks as shown in figure D and E. These marks are called as a Prewitt operator. A slight variation of the preceding two equation uses a weight of 2 in the center coefficient, that is g of x is equal to del f upon del x is equal to first bracket z7 plus 2 z8 plus z9 minus in second bracket z1 plus 2 z2 plus z3, and g of y is equal to del f by del y is equal to first bracket z3 plus 2 z6 plus z9 and minus second bracket z1 plus 2 z4 plus z7. It can be shown that using a 2 in the center location provides the image smoothing. The figure F and The figure F and G shows the mass used to implement these equations. These both the equation. These marks are called as a Sobel operator. The pre-weight marks are simpler to implement than the Sobel marks, but the slight computation difference between them is typically not an issue. The fact that the Sobel marks have the better noise suppression, that is smoothing characteristics, make them preferable because, as mentioned in previous section, that noise suppression is an important issue when dealing with derivatives. Note that the coefficient of all the marks in this figure is a sum to 0, thus giving the response of a 0 in areas of a constant intensity as expected of a derivative operator. The mass just discussed are used to obtain the gradient component gx and gy at every pixel location in an image. These two partial derivatives are then used to estimate the edge strength and direction. Computing the magnitude of the gradient requires that gx and gy be combined in the manner shown in figure. However, this implementation is not always describable because of the computational burden required by square and square root. An approach used frequently is to approximate the magnitude of the gradient by absolute values. Mx comma y is nearly equal to magnitude of gx plus magnitude of gy. This equation is more attractive computationally and it still preserves relative changes in intensity level. This price paid for this advantage is that the resulting filter will not be isotropic, invariant to rotation in general. However, this is not an issue when the marks such as Primit and Sobel marks are used for compute gx and gy because these marks are give isotropic result only for the vertical and horizontal edges. Result will be isotropic only for edges in these two directions, regardless of which of the two equation is used. It is possible to modify the 3x3 marks as shown in figure so they have their strongest response along the diagonal direction. This figure shows the two additional Privet and the Robel marks needed for detecting the edges in the diagonal direction. This figure illustrates the absolute value response of the two components of the gradient, magnitude of gx and magnitude of gy, as well as the gradient image formed from the sum of these two components. The directionality of the horizontal and the vertical components of the gradient is evident in figure B and C. Note for the example how strong the roof tile, horizontal brick joint and the horizontal segment of the window are in figure B compared to the other edges. By contrast, the figure C favors the features such as vertical component of the facade and windows. It is a common terminology to use the term ramp map when referring to an image whose principal features are edges such as gradient magnitude images. The intensity of the image in figure A were scaled to the range 0, 1. We use the values in this range to simplify the parameter selection in the various methods for the edge detection discussed in this section. In general, the angle images are not as useful as a gradient magnitude of image for edge detection, but they do complement the information extracted from an image using the magnitude of the gradient. For instance, the constant intensity areas in figure A, such as the front edge of the sloping roof and top horizontal bands of the front wall, are constant, indicating that the gradient vector direction at all the pixel location in those regions is the same. The original image in figure A is of reasonably high resolution, that is 834 by 1114 pixel, and at the distance the image was acquired. The contribution made to image detail by the wall bricks is significant. This level of fine detail often is undesirable in edge detection because it tends to act as a noise, which is enhanced by derivative computation and thus complicates the detection of the principal edge in an image. One way to reduce the fine detail is to smooth the image. The figure shows the same sequence of image as in above figure, but with the original image smoothed first using the 5x5 averaging filter. The response of each mark now shows almost no contribution due to the bricks, with the result being dominated mostly by the principal edges. Then the evident in above figure and this figure that the horizontal and the vertical Sobel marks do not differentiate between the edges oriented in the plus minus 45 degree direction. If it is important to emphasize the edges along the diagonal direction, then one of the marks we used in this figure. Then our next topic is combining the gradient with thresholding. The result in above figure shows the edge detection can be made more selective by smoothing the image prior to computing the gradient. Another approach aimed at achieving the same basic objective is to threshold the gradient image. For example, as shown in figure A, shows the gradient image from above figure D thresholded in the sense that the pixel with the values greater than or equal to 33% of the maximum value of the gradient image are shown in white, while pixel below the threshold value are shown in black. We see that there are the fewer edges in the threshold images and that are the edges in this image are much sharper. On the other hand, the numerous edges such as the 45-degree line defining the far edge of the roof are broken in the thresholded image. When the interest lies both in highlighting the principal edges and or maintaining as much connectivity as possible, it is a common practice to use the both smoothing and thresholding. Figure B shows that the result of smoothing, which is the gradient of the smooth image. This result shows a reduced number of broken edges. For instance, compare the 45-degree edge is in figure A and B. Of course, the edges whose intensity values were severely attenuated due to the blurring, for example, the edges in the tile roof, are looking to be totally eliminated by thresholding. We return to the problem for broken in a above section. In next section. Today in this lecture we have discussed about the different type of edge detections, basic edge models. Thank you.